thank you for rejoining, everyone. And so I'll jump into my second lecture, which I call betting protocols. So this lecture is a little different. It's really designed to, it's about how we really put these ideas formally into game theory. So I won't be reporting on mathematical results for the most part, but I'll be saying just how do we set it up? And that will prepare for the lectures for tomorrow. And also, hopefully, it'll make it a little easier for you to, I hope so, you'll become readers of our books, my books with Volodya. And this introduction to betting protocols should enable that, should make the book a little less intimidating for those not familiar with the topic already. So I'll talk about, first I will make some general comments about game theory, explain how what we're doing here is really uses a very small part of game theory, but what it does use. Then I'll show how we use these ideas to test a probability, how we formalize in game theory the testing of probability distribution, more generally the testing of a probability forecaster, how we would test, how we introduce the idea of one-sided offers and suboptimal bets, how we use signals, and how we would test market efficiency. So to make this testing by betting mathematics, to make it rigorously mathematics, we have to define a game. What, according to game theory, what do you have to do to define a game? You got to say who the players are. Well, we seem to have players here. We have the person betting and the person we're betting against, but that's not the whole story. So we need to fill that out. Who are the players in this game? How do they move? What are the rules for whether they move? Whether they move simultaneously or one after the other, what information the players have, and what the players are trying to achieve, what their goals are. Those are the elements of a game, according to game theory. So let's see what they are. Now, in if you've studied game theory, you probably studied games of imperfect information. In economics, those are the games we're interested in. The different players in an economy don't see always what each other are doing. They move simultaneously. Their moves are hidden from each other. That's what most of game theory has been about since the work of von Neumann and Morgenstern. Von Neumann's minimax theorem, proven in the 1920s, and then his book with Morgenstern, published in 1944. And then after that, the idea of Nash equilibrium became popular, and the game theory became very popular in economics. Even before that, it was popular among people in doing, intellectuals in the defense industry. So all of these people were using mainly games of imperfect information, which means the players didn't see each other's moves. This game theoretic probability uses an older but very narrow part of game theory, two-player games with perfect information. Now, we sometimes have more than two players, but we focus on what one player can achieve. So the one player is playing against the others as a team. The others are a team. So the forecaster is, well, we'll see who the players are and where that works. But the point is that even though we have many players, we focus on trying to find out what one player can accomplish. So that means that we're looking at games that are two-player games, and also they're perfect information. Everybody moves in order. And that's a very narrow area of game theory, and it's actually one that is older. Goes back, it's been studied, there have been actual mathematical theorems. You could say the other game theory. You could trace the theory of oligopoly by Cournot in the 1830s is sometimes considered a game theory. So I won't say the perfect information games are the oldest, but they were studied mathematically in long before von Neumann and Morgenstern. So here is a theorem that's relevant to the kinds of games we're studying. It's Zermelo's theorem, proven by Zermelo in 1913. And he proved that in a two-person perfect information game that always has a winner. So all the possible outcomes, it's always has a winner. One of the players has a winning strategy. Now, he proved this for games that finite horizon games, you could call them, games that end after a finite number of steps so that you can say who the winner is. For every end point, which one is the winner? So here's an example between player 1 and player 2. So player 1 chooses one of these 3 steps. And then player 2, if player 1 chooses to go down here, player 2 chooses between these 2 alternatives. If player 1 goes here, player 2 chooses between these 3, and so on. So these are the possible ways the game can go. Each path is a final outcome. And if the game takes this path here and you end up there, red, player 1 wins. We say all the outcomes marked with red are the ones where player 1 wins. Those marked with green are the ones where player 2 wins. So this this diagram is supposed to specify the players, 2 players, the rules for moving. Here's how they can move at each step. The information the players have. And the information is that each player sees what the other player did before. This is a perfect information game. Who has a winning strategy? Zermelo says one of the players has a winning strategy. And we can prove Zermelo's theorem by just looking at this example. Why is it that one of the players has a winning strategy? Maybe you've seen this before, but the proof is by backward recursion. You look at the endpoints. Here, in this situation here, whose turn is it? It's player 2's turn to take one of these choices. So player 2 is going to choose green. Is going to move here or here, so he'll win. So that means that he's really already got a winning strategy here. At this place here, it is player 2's turn, and to go, well, let's see. Player 1 gets to decide here whether he's going to go there or there. So he's going to choose the red one. He's going to go there. So he actually wins there as well. So we can take off these 2 branchings. Also down here, we may as well take this one off too, because here player 2 is deciding. So he's going to choose green because he wins when you have green. So you can take these pairings off. I forgot about taking this one off. I'm leaving it there. And we reduce the tree to something like this. Okay, now let's take off some more. Let's take off, we have this tree here. Let's take off these up here, and let's take this off. So we successfully take off the terminal nodes by looking at who is making the decision and what they would decide. Here, the player 1 would choose to go in one of these 2 directions. So he's already got a winning strategy here. And in this case, green, all of them are going to green. So green is already won here, basically. So that reduces us to this tree. And then we take the next step and we see that we get down to this tree where player 1 has got to decide to go in a direction where red wins, that is where he wins, or where green wins, which is player 2. So he's going to choose to go to the red. So player 1 has a winning strategy. And you see, if the game is, if the tree is finite, you can always do this. Work back from the terminal nodes to see who would do what until you come to the very beginning, and then the first player to move. If he has a choice, the first player is going to choose to win. If he doesn't have a choice, it's already over. The other player's won. So one of the players has a winning strategy. When we looked at this game originally looking like this, it probably wasn't obvious to you who had a winning strategy. It wouldn't be to me. But when I can study a little bit, I see that player one, red, actually has the winning strategy. So in the next lecture tomorrow morning, well, it's morning for me, I guess, afternoon for you. Tomorrow, I will show, what will I do tomorrow? I will show how the theorems in probability theory, like the law of large numbers, become theorems in game theory. And we're going to be in this context of a two-person perfect information game. So the theorems like the law of large numbers say that with a high probability, the frequency will approximate the probability. So that's the law of large numbers assigns to a certain event the probability 1 minus alpha, where alpha is a small number. And we prove that by showing that the bettor has a strategy that multiplies his capital by 1 over alpha unless A happens. That's going to be our definition of probability in game theory probability, and it's about the existence of a strategy. And either, if that is the goal, if the goal is for the bettor to multiply his money by this much unless A happens, otherwise he would lose his money. If that's the goal of bettor, and bettor is playing against the other players, either bettor has a strategy for doing that because he has a winning strategy, or else he can't do it because the other players as a team have a winning strategy. So it becomes a question in game theory whether this is true or not, and we will prove. And will we prove it? We'll explain that we can prove it in game theory. So that's some of the theorems involve showing that a certain event has high probability. Others involve in infinitely, games that go on infinitely, we can sometimes prove that certain events have probability 1, meaning the bettor can multiply their capital infinitely unless the event happens. So that's the general idea of how we fit into game theory. So in a two-person, in the usual games of imperfect information, in order to get a Nash equilibrium, you have to have mixed strategies, which means that you don't have to prove being able to accomplish something, you accomplish it by betting at random, by choosing a strategy that tells you to, by at random, choosing different strategies. A pure strategy is where you don't behave at random. You just follow a definite strategy. And in our case, these perfect information games, or Mello's theorem says there is a pure strategy. That's what this means. By winning strategy is a pure strategy. You don't bet with randomly. You follow a certain rule for how you're going to bet based on how the other players have played. So the idea is that to prove theorems in probability theory, or in the generalization of probability theory that testing by betting can accomplish, we only need pure strategies. But I want to emphasize that this doesn't mean that you have to have a strategy to play the game. To test, you may not, our idea of testing by betting allows us to bet without a strategy, because we may not know what the forecaster is going to do. So we don't have to start out with figuring out all the different things the forecaster might do and coming up for a strategy for it. No, we can just bet by the seat of our pants as we go along, think it through as we go along. So the fact that we prove mathematical theorems using pure strategies doesn't mean that we have to have a strategy for betting. That's a different thing. Our fundamental principle, remember, we're not relying on standard probability theory. We have a fundamental principle of our own for testing by betting, and it says you can just keep betting as long as you don't put more money into the game. And you could still discredit the forecaster by multiplying your capital. So you can bet without a strategy, even though the theory, when we replicate standard probability theory, we're talking about strategies. So our betting, so I want to introduce here the idea of a betting protocol. That's what this slide is about. This here, I already said it, what we have to do to specify a game. A betting protocol does part of that. It does 1, 2, and 3. It does, the betting protocol doesn't say what the goal is, but it says who the players are, how they move in order, given by the protocol, and what the information they have. And the information is what has happened in the, well, what it says is, it doesn't say they don't have other information, but it says that they do have the information about each other's moves so far, and they don't know what the other players are going to do in the future. But the goals, we can use different goals with a given protocol. So a protocol partly specifies, in the case of a perfect information game, we partly specify the game by specifying a protocol. The many of the examples I have here are in our books. Some of them are in the Royal Statistical Society paper that I talked about in the previous lecture. So first, a protocol for testing a probability distribution. Here is the protocol right here. This is just the name of it. So the protocol has 3 steps. It says that the skeptic, so the skeptic is the name of the person who is doing the testing. We call the first person a skeptic because he's testing the probability distribution. Now, we will introduce in a moment, I'll bring in the forecaster, but I don't need the forecaster here because the forecaster, before the game started, the forecaster said, my forecast is this probability distribution on this sample space. Why? So skeptic is going to announce a bet, and that's S. But he's going to make his, and his bet is just like we were saying informally. So this just formalizes what I was saying in the first lecture, that a bet is a random variable, that is to say a function on the sample space that is non-negative. It maps the possible outcomes to something, a non-negative number. It's a non-negative, the bet's outcomes are non-negative, and the expected value under the hypothesis is 1. And then reality announces why. So we have to have a player who makes the announcements. And in our books, we've always used the name reality for this player. Some people might prefer the name nature. But the problem with the name nature is that people think nature has laws. And here we want to emphasize that our game doesn't make any assumptions about nature, about reality, excuse me. And whatever, que sera, sera, what will happen, will happen. That reality is, it's reality. So our name of our player that settles things is reality. You could say it's God, but then God might be controlling the better too. So let's say this is reality, which is outside the person betting. So then the outcome, the capital, K is our capital, and the capital started out 1, and now it is the betting score. So S is the bet, S of Y is the betting score, skeptic is the person testing the probability distribution, and the goal is to make S of Y large. But there's an underlying goal, of course, is that maybe skeptic is not really, maybe his real goal is to find out whether the probability distribution and reality agree. Maybe this probability distribution was made up by skeptic himself. Maybe skeptic is also the forecaster. This is my model. I'm making up this my model, but I better check it. I better check whether it works. I better bet against it to see whether it works before I put it out to the public. So our real motive is science here. We're trying to find out whether the probability distribution agrees with what comes some consistency with what reality does. But for that ultimate goal, we're going to, in order to figure that out, our intermediate goal is that we try to bet in a way, try to do our best to make the betting score large. Okay, so this is our first example of a protocol. Now, I want to emphasize the generality. This is the probability space, could be any probability space in the sense of probability theory. So the outcome Y is not a single number. Not a finite, the space Y isn't necessarily finite. It could be continuous, though I use finite examples, discrete examples. Y could be continuous. It could be multidimensional. We could have a stochastic process in question here. P could be the probability distribution for a stochastic process. So this is a very general picture, as general as all of probability theory. And also I want to emphasize what is meant when I say that it is a perfect information protocol. I mean, the players move sequentially. First, skeptic moves by making his bet. Then reality announces the outcome. And reality sees what skeptic did. Okay. Each one sees the other's moves as they are made. So this is completely general, but of course a special case is heads and tails or red and black, which is what people bet on in casinos in the 19th century. In that case, there is some probability for heads. Let's say heads is 1 and tails is 0. There's some probability P for heads. And how would we make this general picture? How would we make this special case, this specialization of this general protocol? What would we do? Well, a bet in this case really just gives that Y only has 2 elements in it. Script Y. Script Y is a set of 2 elements, 0 and 1. So we just need to give the S, the capital S, we just needs to give its values for 0 and 1. We could call that S0 and S1. And to say that the expected value is 1 means that the probability of 1 times the payoff if you get 1, plus the probability of a 0 plus the payoff if you get 0 adds up to 1. So that's what this relation here reduces or is re-expressed in this way. And then reality announces one of 2 things, a 0 or a 1. And the outcome is either S1 or S0. If Y is 1, then you get S1 because 1 minus Y is 0. If Y is 0, you get S0 because Y is 0 and 1 minus Y is 1. So this is just a way of writing this protocol. So you see, we have this very general protocol, but when we get to particular examples, it takes on a different look. And that can be confusing, and sort of the first step in understanding our book is just reading these things. That's why I'm going to spend a lot of time on this in the hope that you all become readers of this book. So here I reproduce what I had on the previous slide. Slow me down, Marco, if I'm going too fast or I need to pause on something and somebody is asking a question.
All good, all good, yeah.
So here I have taken this protocol and just written it in a different way because sometimes we find it convenient to write it in a different way. So what is my way here? Here, instead of saying that I'm announcing 2 numbers, I just announce 1 number. Why is it? Well, these 2 numbers are not, if you told me what S0 is, because everything in this equation only has 1 degree of freedom, if it were. If you tell me what S0 is, I can solve for S1. I can solve this equation for S1. You tell me what S1 is, I can solve for S0. So there's not really a need here to give 2 numbers. I can just give 1. So let me give a number M which is equal to S1 minus 1 over 1 minus P, or it's also equal to 1 minus S naught over P. Remember, P is given. P was announced at the beginning. It's part of the story. The forecaster has said, before we started the story, before we wrote down the protocol, the forecaster said, my forecast for heads is P. P is the number between 0 and 1. So P is known. So telling what M is the same as telling what S1 or S naught is. And what are the possibilities for M? Well, S naught is less than 1. So M has to be less than 1 over P. S1 is less than 1. So M has to be bigger than minus 1 over 1 minus P. So M is between those two numbers. And then if you figure out what this equation is going to be in terms of M, it's equal to 1, our initial capital, plus M times Y minus P. There's another way of writing the same protocol. So it might take you, you could spend a little time doing the algebra to see why this is equal to this. But it's a convenient way of writing this protocol because we can generalize it to other protocols. You see, here is the outcome minus its probability. And what we're doing is we're getting some multiple of that. If the skeptic chooses M, M can be a negative number or it could be a positive number. If M is positive, then you're betting on heads. You're betting that Y will be 1, because if Y is 1, this quantity is positive. 1 minus P is positive. If Y is 0, this is a minus P, it's negative. So you choose M positive, that means that, and you want to increase your capital. So choosing M positive is saying that you're betting on the outcome heads, but you can make M different amounts, and that means how much of your money you're betting that time. Similarly, if you choose M negative, then it would cancel out a negative outcome here, and it means that you would be betting on tails. So when you bet M negative, you're betting that Y will be equal to 0, or you're betting on tails. But you're constrained by how big you can make your bet by the constraint that you aren't allowed to risk more than your initial $1. That constraint is built into these protocols. We don't always do that. We don't always build that constraint into the protocol, but here it's built in, that you can only risk the $1 that you start with. And here you're trying to, here this shows that you're trying to add to that $1. Okay. So let me specialize the story to P equals 1/2. So I had two versions of the protocol on the previous slide. And here, all I have done is replaced P by 1/2. So P times S1 times 1 minus plus 1 minus P times S naught. P is 1/2, so I just get the average of S1 and S naught there. And then the payoff is Y times S1 plus 1 minus Y S naught. That's still the same. Down here, 1 minus 1 over P. Well, I've rescaled it. I said M had to be less than P, but I've sort of, to make it convenient, why did I do this? I say M is between -2 and 2. Oh, okay, it is. Yeah, because P was 1/2, so 1 over 1/2 is 2, right? So when I would put P equal 1/2, I get a 2 here, -2 and 2. So M can be between -2 and 2, and now the payoff is your initial $1 plus M times Y minus 1/2. Okay, so this is just what we had on the previous page, where P is replaced by 1/2. Now here's another way of doing it. So maybe this is kind of boring. I'm just looking at different protocols. But it's useful if you want to actually read this book, which okay. Testing for the probability 1/2. I'm going to take this protocol and I'm going to rewrite it in another way. I'm going to, instead of having 0 or 1 as, instead of coding heads and tails as a 1 or a 0, I'm going to code them as 1 minus 1. That is sometimes convenient. So when you redo things in that way, then M, the amount you bet, is going to be between -1 and 1. If you do it that way, then this becomes very simple. It's 1 times the amount you bet times either a 1 or a -1. You see, if I kept this -2 to 2, then this would be more complicated. It would be M times 1/2 Y. No, so we want to make this simple. And we do that by constraining M between -1 and 1. So this protocol has the same meaning as this one, even though the M down here is twice as big as the M up here, but you can choose M to be anything in that interval. So it's the same set of options. Skeptic has the same set of options here as here. So this is another equivalent protocol, another way of doing it. And we switch between these different things depending on the context and what we want to do. This one is a very nice one for generalizations beyond probability theory. So now, if that's all clear, stop me if it's not. Let's talk about testing a probability forecaster. So up here, we were starting with the probability distribution and asking whether it's a good description of reality, basically. Now we're going to have a forecaster, and the question is forecaster a good forecaster? So now what happens is we put forecaster in here, and forecaster, the first step is that forecaster announces the probability distribution, and then we do the same thing we did before. Now, really, this is just another way of saying the same thing, because here we just built forecaster's forecast into the name of the protocol, but here we had forecaster actively announcing it as part of the game. Doesn't really make any difference, except it's a psychological shift. Because now up here, it made it look like P belongs, we were accustomed often to thinking that if we're talking about objective probabilities, we're accustomed to thinking, oh, the probability is part of reality, it's part of nature. But here it's clear the P belongs to the forecaster, and not to reality. And that's a psychological shift. Now, if P is a probability distribution given by quantum mechanics, say, or some other well-known theory, then all the forecaster is doing is saying, I believe this theory, I adopt this theory as my probabilities. So I am forecasting, I am playing the role of quantum mechanics. And so I'm quantum mechanics. In that case, it looks like, we think of quantum mechanics as part of nature. We can go back to this probability being nature if we want to, but this formulation is more general. It allows forecaster to be just the guy down the block. It allows a forecaster to be Nate Silver forecasting on his website. It allows a forecaster to be the weather forecaster or the National Weather Service, the United States, forecasting hurricanes. There's a psychological shift. And so in game theory probability, this is the way we think. We think of forecast, a probability distribution is not something we're trying to give an evaluation of the connection with reality. It's not just my opinion. It's not just good enough because it's my opinion. It's got to fit what happens. It becomes, even though this in a sense is a theory, this testing thing makes this into an objective theory, just as objective as what statisticians are usually thinking when they test things. But psychologically, we've given it this subjective nature, in the sense that there's somebody asserting it, the forecaster. Okay, now we do something serious. Instead of having one step, we have many steps. We start with $1. Now, K0 is our initial capital. I didn't say that here. I took it when I said the expected value of the payoff had to be 1. I had in the background the idea that I start with a $1 or £1 sterling as my capital, or €1 or whatever. Here, I make it explicit that the initial capital is 1. And then forecaster, and then we have N steps, capital N steps. Each time forecaster announces a probability distribution, on the little nth round, that his announcement is called P sub n. And then skeptic announces a bet against that probability distribution. And reality announces the outcome. And then skeptic's new capital is his bet's payoff. Now notice he's used all of his current capital. His current capital is Kn minus 1. On the first step, that's just 1. But on the next step, it's something different, according to this rule down here. So he is now allowed to, what he now does is he makes a bet that uses all of his capital. But no more. That's all. His bet has to have expected value equal to his capital under the forecaster's probability distribution. So then, okay, so this is still a perfect information protocol, which means that on each round, each player sees, forecaster makes a move, skeptic sees it, and reality sees it. Skeptic makes a move, the other players see it. Reality makes a move, the other players see it. So at each play, and then you go to the next round. So at each play, the player making the move knows what everybody else has done before. But still, we're outside standard probability theory because we didn't start with a joint distribution for y1 up to yn. On each step, the forecaster told us a new probability distribution. And the forecaster is acting freely here. And so is the skeptic. People don't have to be playing with a strategy. The forecaster might not even have decided what experiment he was going to make before he saw the outcome of the first round. He might be playing a strategy. So we'll talk about that. But let me compare this protocol to a protocol where skeptic has, excuse me. Let's think about the case where skeptic has a strategy. What would it, I'm sorry. I need to listen to myself better. I'm now going to talk about strategies for forecaster. Let's suppose this forecaster has a strategy. His strategy tells him what probability distribution to give the first time, and then after he has seen reality's move, what probability distribution he is going to give the next time. Well, what would that strategy look like? One way would be to say that actually what forecaster has is a joint probability distribution for all n moves by reality, all n random variables. He has a joint probability distribution for it. And we use that joint probability distribution to give the conditional probabilities. We calculate from that joint probability distribution, we calculate conditional probabilities at each step given the previous moves by reality. we calculate the conditional probability of skeptics' announced strategy as a function of the move on that round. And that's, we have to make that equal to our current capital. So this becomes, if we do that, if we fix a strategy for forecaster, then we can take forecaster out of the picture because he doesn't have anything to do anymore. His moves are determined, are specified by the strategy. So we take him out and we get this picture here, which is a picture for testing a joint probability distribution P. Now, my presentation of this slide has been a little bit of garbled. I kind of started at and moved backwards. But what I've tried to get across is the idea that a probability distribution for a stochastic process can be regarded as a strategy for forecaster in this protocol. In this protocol for making successive bets, where each time forecaster announces a probability distribution. In this protocol, if you give a strategy to forecaster, that's like giving a joint probability distribution. They're the same thing. A joint probability distribution for the stochastic process is the same thing as a strategy for forecaster in this protocol. So once again, we have a psychological difference in the way we're thinking about it. Often people think probability distributions are telling reality what to do or telling nature what to do. Nature chooses according to the probability distribution. That's the way I think we're all taught, or we get the idea from somewhere. That's in our culture now. But game theory probability says, think about it in a different way. Probability distributions aren't telling nature or reality what to do. They're telling forecaster what to do. They're a strategy for forecaster. Then the question is whether forecasters' forecasts are consistent with what reality is doing. So it's a slightly different way of looking at what we're doing. Okay, now I want to step outside of standard probability theory to show this framework is broader. So one thing we could do is make betting offers. We're now getting into imprecise probability. If we make the betting offers more limited, let's say we only allow one-sided bets. Instead of letting M be between -2 and 2, which we did before, let's say M can only be positive, which that means we only allow skeptic to make positive bets. We only allow skeptic to bet on heads. We only allow skeptic to bet on heads. So we say we're setting odds, 50-50 odds, but it's one-sided. In some sense, we're saying, well, the probability for heads is at least 1/2. You can you can take my 50-50 odds, provided you bet on heads. You can't, so that's, this could be regarded as an example of imprecise probability. There's another thing we could do that really has nothing to do with imprecise probability, but we could take this general protocol that we had on the previous page, this protocol here, where we say, okay, at each step, you've got to take your current capital and your bet's expected value has to be equal to that current capital. Instead of doing it that way, we could say, well, the bet's expected value could be anything less than or equal to the current capital. But you're still just going to get the payoff from that bet. the capital you didn't use by making, if you choose to make this less than your current capital, you're really wasting money. And you don't get it back because all you get is the payoff on your bet. So you are wasting money. Skeptic is giving up money. Skeptic is giving up money. Why would skeptic want to waste money? Well, probably skeptic doesn't want to waste money. But in our theoretical work, sometimes we want to make bets to prove something. We want to make bets where it's too hard calculating, getting our bet to be exactly, the expected value of our bet to be exactly equal to our current capital is too hard. The calculation is too difficult. Maybe the calculation is impossible. You know, if we get into looking at this from the point of view of, you know, computability theory, maybe the expected value, exact expected value of the bet is not computable. So we can't be, you know, we can't be sure we get exactly equal. So all we can do is make sure that it's less than or equal. And then it's a legitimate bet. So for that reason, it's better to relax and allow less than or equal. And for those of you who know a lot of probability theory, I will say here something that I'll explain more to everybody later. For this reason, the fundamental tool in our advanced theory that we'll do tomorrow, instead of being martingales, it's super martingales, because we want to allow this inequality. Okay. The next topic is using signals. So this is very common in all applications. In statistics, we would call the signal an independent variable. In engineering, it's sometimes called a signal. In machine learning, it's sometimes called the object. Y is the label, X is the object. Anyway, in this game theoretic framework, we put it into the game. We have reality announce a signal. Then forecaster announces a probability distribution. Then skeptic announces a bet and reality announces the outcome. Now here I have reality announcing the signal. That's not really important. We could have anybody announce the signal. The point is that the signal is announced before these people move so that it's clear they can use it as part of their thinking. If they're going to follow a strategy, they can use that information as part of their strategy. Remember, it's a perfect information game. At this point, forecaster knows what X is, so forecaster can use X to decide on his bet, on his probability distribution. Skeptic can use X to decide on his bet, and so on. Now, as I said, anybody could actually do this announcement. I give it to reality because, you know, reality does everything. Reality knows everything. So it's convenient to say it's reality. It could be an experimenter who's fixing some aspect of the experiment. It could be that experimenter could be the same thing as the forecaster, or the experimenter could be the same person as the skeptic. But generally just say, okay, it's reality that does it. The important thing is that it's already done. Now, I should interject here the point about when we say the term perfect information game, we aren't saying, what we are saying is that each player knows all the other players' preceding moves. We might allow the player to know other things too. In a perfect information game, it is not excluded that there's other information. So this information might have been here anyway, but by putting it explicitly in the game, it allows us to talk about strategies that use it. Okay. So when we have this signal, what does a strategy for forecaster look like? Because now forecaster can use everything that came before, all the preceding moves. He can use all the signals, including the signal on that round, because he moves after the signal for that round. But he's also got all the preceding outcomes and all the preceding signals. So he uses them to specify a probability distribution. Or if he had a strategy, that strategy would specify a probability distribution for every possible sequence of that preceding moves. Not just the ones that actually happened, not just the ones that are actually happened in the game so far, but for all the ones that could have happened. A strategy, that's what a strategy in a game has to do. It doesn't just tell you what to do at each step. Well, yeah, a strategy doesn't just come into the story at each step and say, do this. A strategy says in advance what you're going to do no matter what happens. Or that is to say, for each possibility of what happens, it tells you what to do. So for all the different possible values, x1, y1, up to xn minus 1, yn minus 1, and xn, it's got to give a probability distribution. That's what a strategy for forecaster would look like. This is also outside standard probability theory. Probability theory doesn't really deal with that in standard probability theory because you've got this rigid framework. Kolmogorov's axioms, Dub's filtrations. You've got to have one big probability space. So this is outside standard probability theory. It's not outside standard statistics because actually people try to have we pretend that there's a more unified people in probability and statistics pretend there's a more unified picture than there really is. But really, statistics goes outside of standard probability theory in a number of ways, and this is one of them. They look at models which specify essentially strategies for forecaster in this kind of situation, which is something that's outside standard probability theory. Each of the separate moves, each of the P's is a standard probability distribution, but the whole picture is outside standard probability theory. It's in statistical theory. Statisticians, I have a PhD in statistics. A fellow statistician said to me, a young woman, the point is not that she was young, but that she was, the point is not that she was a woman, but the point is that she was young. And she'd heard of Glenn Shafer. Oh, that's a Dempster-Shafer theory. And now he's doing this other weird stuff. She said, now, you're not a statistician, are you? And I said, well, goodness, I got a PhD in statistics. If I'm not a statistician, what am I? Am I an engineer? Well, I'm a business professor. Okay, but I'm not an accountant. I'm in an accounting department, but I'm not an accountant. Am I a computer scientist? Well, my PhD's in stats. So if what am I, if you want an identity, I'm okay. But anyway, statisticians as a statistician, I and the other statisticians give lip service to probability theory. We say, yeah, we use probability theory. And we send our students to study major theoretic probability theory. Maybe, at least if they're PhD students, they should take a course in it, but we don't. After that, come back and do your work. So we have a kind of a lip service to it, but we actually go outside it. And so imprecise probabilities goes outside it too. And imprecise, if statistics as a discipline has a future, I think I said this already, it needs to absorb the ideas of imprecise probability and use them. And this is one one respect in which maybe statistics is already using the ideas of imprecise probability. I'm not the first person to say this. I think other people that have tried to sell imprecise probabilities to statisticians have been saying. So I've already said this, haven't I? That there's a psychological divergence between probabilists and mathematical statisticians. By the late 20th century, mathematical probability meant Kolmogorov's axioms. You have this very difficult, I don't know if any of you looked at this. Excuse me, I know some of you looked at it. I don't know how many of you have looked at the definition of conditional expectation. It is, statisticians never use it well. Very mathematical statisticians publishing articles in top mathematical statistics journals use it, but applied statisticians never use Kolmogorov's definition of conditional expectation. It's too unnecessarily hard because it's unnecessarily general. A conditional expectation is only defined up to measure zero. So it's not really it doesn't tell you what the answer is exactly. So in applied statistics, you do it in a way in which there is an exact answer. This is very abstract. But in this abstract picture of the probabilists have, all probabilities are inside one huge probability space. It's so huge that it describes the entire evolution of the universe. And although, this has been very influential, and a lot of statisticians actually think this way too. I would be curious if we have soon I'll kind of have another little question session. I'd be curious about whether you think this way, whether you think there's some true probability distribution that is governing the whole universe. Obviously, I'm not thinking in that framework right now. I've already said this too, that this picture has infiltrated some applied work, but applied statisticians go outside of it. This idea of the x's, the fixed x's, that's in the basic way statisticians do regression or least squares since the 1920s. Before the 1920s, regression was kind of something where you had a joint distribution for the x's and y's, but Fisher showed how to do the theory where the x's were fixed, even though they're not really fixed. This is going outside the probabilist folk picture. Combining p-values in Fisher's method, statisticians do this even though they don't have a global probability distribution for what experiments are going to be conducted, because the next experiment you only may think of it after you do the first experiment. It may be some new brainstorm that you come up with. Statisticians who take a subjective view of probability theory tend to reject this folk picture. Imprecise probability people use less than a probability measure. So game theory probability is doing that too. These two slides are just meant to bring out this difference with the way the probabilists are thinking. So I want to say a few words about testing market efficiency. I won't go into details, but I want to show how it fits in to the imprecise probability picture. I don't know if this has become very widespread as in the imprecise, in the SIPTA community. I don't know how many people are fitting finance theory into imprecise probability in this way, but I would like to make this widely understood so more people could. So let's look again at this way of doing heads and tails. Remember, this is the way where we code tails as -1, heads as 1. so that a skeptic can announce a bet just by giving a real number whose absolute value is less than 1, a real number between -1 and 1. And then the capital, the payoff adds to the initial capital. You just add the bet times 1 or -1, the outcome. We could generalize this to many flips. This is the same as this one, except we have many rounds. So each case, instead of the absolute value of m being less than or equal to 1, it has to be less than or equal to our current capital, because we're going to add -1 or +1 of the bet times our bet to the current capital. And so this number here can't be, if it turns out negative, it can't be a negative number bigger than minus the current capital. So we need to keep the new capital positive or non-negative. So we have this constraint. Now let's make one little change. Instead of doing heads or tails, where reality's move space is -1 to 1, -1 or 1, tails or heads, let's let it be any real number between -1 and 1. That's a minor typographical change. And actually, for some mathematical purposes, it's a minor change. But in terms of interpretation, it gives us a vast range of new applications. Because now you can have a forecaster who's estimating these numbers y1 up to yn. So you have numbers y1 up to yn that are bounded between -1 and 1. And forecaster's estimate is 0 each time. That's what this would be interpreted as. We can go to the, then we're going to generalize it to the case where his estimate is not 0 each time. We'll bring forecaster explicitly into the picture. But this is a case where we have a forecaster, special case, where we have a forecaster who sees these numbers coming and says, I think the best estimate for all of them is 0. I think that, like maybe these quantities are the errors from some measurement instrument. And you say, I think my measuring instrument, my forecaster says, I think this measuring instrument is 0. The best estimate of the error might be positive, the error might be negative, but the best estimate is 0. And I think that's always true. So skeptic gets to bet against that. And each time, his payoff, he adds to his current capital. He bets on the error being positive or negative. See, yn is no longer 1 or -1, but something between 1 or -1. And if you choose m positive, it means you're betting that yn will be positive. And that's saying that the measuring instrument is biased in a positive direction. I expect it to be positive mostly, or most often, more often than negative. So I think I'll make money if I bet in this way. That would be the skeptic who is choosing m positive. You might have a different skeptic who chooses m negative. Or you might have a skeptic that averages the two kinds of bets, like we were talking about before, to get a kind of who doesn't know which way it's wrong, but thinks it's wrong, or is betting that it's wrong. Now we can make this, is this my last slide? No, this is my next to last slide. We can make this more interesting by allowing the forecaster to vary his estimate. So now what do? The forecaster announces some number, which is going to be a forecast of an outcome y. And we know forecaster is good enough that he always is within 1 unit of the truth. Now we could make this 1 a bigger number. So there's some limit on how much the forecaster could be wrong. That's all we need here. but since we make the possible error is bounded by 1, so that means we can make a bet here that's as big as our current capital in absolute value if the payoff is going to be the estimate minus the outcome. The estimate here, M, the difference between it and the current outcome is our payoff. So this looks just like, we saw something like this before when we were doing probability. When we were testing a probability, we had the payoff was the current capital plus the outcome, 1 or 0, minus a half. Or more generally, it would be minus, we went back before, it was minus P. Down here, we had the amount bet times the outcome minus the probability, which is the prediction. So what we've done is we've generalized from heads and tails. Here, we're generalizing from heads and tails to estimating some number. And we're betting against that estimate. And we're taking that estimate to be an offer to bet. So this is very broad because there's all kinds of people out there giving estimates of things who aren't being tested. We're not doing a good job of testing financial analysts who claim to have foresight and knowledge that will allow them to estimate what a company is going to do, what its earnings are going to be, or what its dividend is going to be. We have all kinds of supposed experts that are estimating things and they aren't being tested. So this is taking the idea of testing in statistics and generalizing it to those stories. Now, if we take one more twist to this, we can get a way of testing efficiency of a financial market. So forecaster, up here, we have forecaster announcing the estimate. But when we're looking at a financial market, the idea, I've said it before, is that today's price is an estimate of tomorrow's price. So now we don't need forecaster. Forecaster and reality are both replaced by market. So market is announcing the price today, that's Y, and market also announced the price yesterday. So we take yesterday's price as our M. That's the idea. Now, the only complication is this max here. But if you took away the max of Z over 0 and Y, and just look at this part, it looks the same as this. We've just taken the previous. See here, we've just replaced MN with YN minus 1. We replaced MN with YN minus 1 down here, and also in these two places. But here it got a little more complicated. Why is it a little more complicated? It's because the price of a financial security, let's say the price of a stock, the price of a stock is only bounded below, theoretically. The price, a stock can go down to 0. That's when the company is bankrupt. But because of the rules for limited liability corporations, the rules mean that a stock cannot take a negative price because that would mean that the owners of the stock, the shareholders, would owe money. But the whole idea of a corporation is that if the corporation goes bust, the shareholders just lose their money. They don't owe anything. So a share price cannot, or a stock price cannot become negative. But on the other hand, there's no limit on how rich the, how well the company can do. Now, as a practical matter, as a practical matter, you could give some bound. The share price in one day is not going to go up by more than some amount, but you got to make some assumption about that. So you've got to introduce an assumption. And if you don't introduce any assumption, then you would have to cut this off below some bound. If it's below some bound, the game is that this is zero. That's the outcome. So this is a little bit artificial just to fit into the stock market story. But anyway, you can make this practical by introducing some realistic bound to how much the stock price could go up in one day. Maybe this is not the right way to write it. So this idea of testing the efficiency of a financial market, Vovk and I have studied it extensively. 4 of the working papers at probabilityinfinance.com study this. It leads to very interesting results. The assumption that you cannot make money in this game implies the properties that we see in stock prices. For instance, they look like Brownian motion because the assumption that you cannot multiply your money in this game by a large factor implies that the prices will look like Brownian motion. It also implies that there will be a premium, what sometimes looks like an unreasonable premium for buying stock instead of bonds. And there's other implications of it. Now, this work we've done has not caught on. Well, there are now some people some mathematicians doing, stochastic calculus, which is kind of the mathematician's version of finance theory, using these ideas. They've got, for instance, Karatzis at Columbia wrote a book on wrote a blurb for our current book. The people who do finance theory as professors in business schools and who publish in the Journal of Finance and the Review of Finance and Economics and Review of Financial Economics, those top finance journals, so-called, or top accounting journals also, have not picked up on this. This does not correspond to their way of thinking. So this way of testing market efficiency is not their way of testing market efficiency. Basically, they've given up on, they have a concept of efficiency that turns out to be not testable. But this is this concept that you cannot, that market efficiency means you cannot, a bettor will not be able to multiply their money by a large factor in the market. Now, in that case, if you take this market efficiency, to be serious about this, we know that over time, investors in the stock market, the market as a whole, over time, people do make money in the stock market. So what the market efficiency hypothesis would actually say is that you can't make money relative to the market as a whole. Or for instance, the S&P 500, the index of the 500 largest company in the New York Stock Exchange, until recently, until the emergence of Chinese mega companies, until recently at least, that represented most of the financial market, most of the publicly traded corporations. So the hypothesis would be that you can't make money relative to that overall market, or for instance, you can't make money relative to the S&P 500. So instead of valuing the stocks in dollars, the stocks should be valued as a fraction of their market capitalization, as a fraction of the total capitalization. So the market, the efficient market hypothesis would be that you can't make money in that numeraire, as people call it in finance. The numeraire is the unit of measurement, which might be dollars, might be euros. That's different because the exchange rate between dollars and euros changes. So you could use dollars or euros as your numeraire, or you could use the value of the overall market as your numeraire. So the hypothesis of market efficiency would be that you can't make money relative to that, can't multiply your capital by a large factor without risking more capital. That would be the hypothesis of market efficiency, and you would test it using these kinds of protocols that I've been talking about. This idea has not gotten a lot of traction in finance theory, hardly any in the so-called regular journals in finance. So I would like to invite people in the imprecise community, imprecise probabilities community, to invade the territory of the finance theorists as well as the territory of the statisticians by adopting some of these ideas. So that's the end of this set of slides. We could have a further discussion in the next 10 minutes, Marco, or we could go back to my other lecture, which I didn't complete. But I'd certainly be delighted if people have some questions they could ask.
Thank you, Glenn. Yes, we do have some questions from earlier. See if I can pick them up. So there's a question from Raimondo. Raimondo, do you want to state your question, or can you unmute yourself?
Yeah, sure.
Thanks.
Sorry. So it's very basic. It's just technical. There are expectations and probabilities. If the space is not finite or not countable, these expectations are meant to be taken with a probabilistic model behind. The bets are also we take expectations over the bets, so they have to be kind of measurable. We don't want to put all this structure, but we want to compute the expectations. So how do we go with it?
So, so we've got to narrow this down to this question down to a particular protocol, I think.
Yeah, earlier on, yeah, around this slide, I guess.
So maybe testing forecaster over time when forecaster announces a probability distribution.
Sure.
So that's right. I mean, if so, if we interpret this as living in kind of Kolmogorov's axiom world, if we interpret a probability distribution as being in Kolmogorov axiom world, then the bet here should be a measurable random variable with respect to P. Yes. And I didn't say that. But I'd rather not live in Kolmogorov measure theoretic world. I'd rather live in the statistician's old-fashioned world where a probability distribution is defined by either a probability density or a discrete set of probabilities, in which case everybody knows what expected value means. Is that a fair answer?
Yeah, sure.
Okay, thanks.
We have a question from Matthias. Matthias, do you want to say the question, or are you there?
Oh yeah, sorry, yeah, I'm there.
Okay.
So I was just making, it was a question or maybe a comment, is that when you say that distributions embody what the forecaster should be doing, right? That's one of the main points that you're trying to get across. Is that basically?
Say that again, repeat that.
So you were saying at one point, and I think that was a very interesting point, that distributions are, so when you specify a P, that's not nature, that's not how nature is behaving, it's just how forecaster is behaving, right? And my question was,
yeah, they are a strategy for forecasting.
Yes, that's right. Is that basically saying that in this framework you embody like a subjective interpretation of probability because different forecasters may have different distributions that they propose?
Yes and no. This is definitely not Bayesian, because it's not saying that the whole meaning of the probability is subjective. But it definitely has a subjective element because you've got, as a practical matter, you've got to choose a, well, let's see. So the strategy is telling the forecaster what to do. Let me answer your question in a different way, Matthias. What if the strategy were quantum mechanics?
Right.
So the forecaster is a physicist, and the forecaster believes in quantum mechanics, and most physicists do. The forecaster believes in quantum mechanics, so he tells you these are the probabilities. Now, is that subjective?
That's yeah.
Yeah,
I guess in
is.
an extreme, I guess, yeah, you could say that's subjective, right? But,
yeah, you could say, well, it's the subjective.
Sure.
The physicist has some subjective probabilities there, but he's being told what to do.
Yeah. Okay, no, I get
quantum
it.
mechanics.
Okay. Yeah.
He's being told by quantum mechanics, you should believe this. And he's like, okay.
Right.
So probability distribution is a instruction for forecaster.
Right. Okay, so you're saying it could embody a subjective probability, but it could also come from some like authority, let's say.
But in any case, we're testing it.
Yeah.
So no matter how subjective it is, we're allowing ourselves to say if it doesn't fit with reality, it may be your opinion, but you don't have a very good opinion.
Yes. Yeah. Okay. Yeah. Thanks. That excellently answered my question. Thank you for that.
But interestingly, there's subjective elements coming from two directions. One of them is a subjective element in the forecaster, but the other is a subjective element in the skeptic because he's got to choose how to bet.
Right.
I think this sort of objective thing is used in too vague a way. It's used in too vague a way. We need to, I think the beauty about the game theory, I mean, in a sense, we've always used games. We've always used betting ideas in probability. And De Finetti's does, De Finetti is always emphasizing the betting idea. But when we put it into the game, when we're precise with the game, it gives us a framework where we can be more clearer about what we mean when we say something is subjective.
Right. When you say that, you mean like disentangling between the forecaster, skeptic, and reality, where the subjective element and the potentially objective elements are coming from.
Yes.
Because reality is arguably the objective. Yeah, I mean, you can't argue with reality. That's
yes, that's the
right.
idea.
Okay, no, that's
reality.
beautiful. Yeah.
Even though we could be predicting the behavior of a person.
Yeah, right. Yes.
So even there, we could have a subjective element.
Yes.
Wonderful question. Thank you.
Yeah, thank you, Glenn.
Very good. So do we want to, I mean, we can continue this discussion, or how long do we have? It's only a few minutes. So I guess we did carry on yesterday well above the limit. So if you really care about telling us more about the topics you skipped at the beginning, I mean, we can carry on, and people can, I mean, we are recording the lecture anyway, so if you want to carry on for a few more minutes, and tell us
Well,
about.
I'll tell you, let me, yeah, I could do something. Thank you, Marco. I still have some energy, and of course I would understand if some of our folks decide enough is enough, but I will, let me share a difference, go back to the,
I'll be very interested to hear more about the interpretation of confidence that you had in the table of contents at the first lecture.
confidence.
That you
Tell me
rather
more.
call differently.
Tell me more what you mean.
Warranties, I think warranties, was it?
Warranties, yeah,
Yeah.
that's how you.
Oh, let me see. I should be able to go to this other. Oh, warranties. Yes, confidence intervals. Okay, I'll say a word about that. This is my, we had these examples, and then I just had a couple slides about warranties. So this is the case where you have a statistical model or a parametric model where theta is the parameter. So instead of having a probability distribution on a single probability distribution, excuse me, instead of having a single probability distribution on the sample space, you could have a parametric class of probability distributions parameterized by theta. This was R.A. Fisher's notation. This is really has really defined the field of statistics almost. What is usually done is the statistician uses the observation theoretically. Confidence intervals are often formed in a more naive way, but the theoretical picture is that the statistician uses the observations to test each of the probability distributions at the same level alpha. And then you look at the subset of the parameter space consisting of the theta such that that pass the test, and that's the 1 minus alpha confidence set. So what is a confidence set? It's a little complicated, isn't it? That's the standard definition. This is, if you read advanced textbooks, that's the way they explain what a confidence interval is. So I won't pause on that, but we could give a betting interpretation. We could interpret each of the tests in betting terms. And so we could say that this alpha level significance test, fixed level significance test, I'll say that again, confidence intervals are based on fixed level significance tests. So that fixed level significance test can be interpreted as a bet that multiplies your money by 20 if you win, right? So you could say, which of the parameter values passed the test in that sense, that you did not multiply your money by 20. And you could say that is a 20-fold warranty set, or in general, a 1 over alpha warranty set. So you just take confidence intervals and reinterpret them as in terms of betting, and you call them a warranty set. So it's just a change of name, except that you can apply this idea when you're outside the probability picture, as we showed with all these protocols, all the ways you can go outside the protocol picture and still bet against hypotheses, because the hypotheses don't give a full probability distribution. So all these other ways of betting against hypotheses, you could also say you have a bunch of hypotheses and you're testing them all, and okay, the ones where you don't multiply your money by 20, that's a 20-fold warranty set. So this gives us a way of generalizing confidence, and generalizing the idea of confidence sets, so that you can get 1 over alpha warranty sets that aren't 1 over alpha confidence sets. This applies even in the case where it looks like you're working in, where this applies even in what statisticians often do, Because remember, I kept telling you, statisticians often move outside abstract probability. Like when you combine successive tests. So if you combine successive tests in the way we're doing it, but you have a number of different hypotheses you're testing as you go along, you can end up with a 1 over alpha warranty set that is where you don't have any way of giving a 1 minus alpha confidence set. So not any reasonable way. And if you try to soup up a way, it actually turns out to be much less effective than this way of doing it. So this is part of the area of application. And I think some of those links on that syllabus that I mentioned go into some practical detail on this. So that's what I had to say about warranties. Marco, do you want to raise a question? Do you want to pursue questions about that? Or I actually have this other section about, which is kind of more fun, that I could spend a few minutes on also.
I don't have questions myself. I don't see. Okay, Matthias is saying now have to. Oh, okay, no, it's just leaving. Okay, thank you, Matthias. No worries. Thanks for coming, being active. Yeah, if you carry on, I'll be happy to hear the also the other section. So yeah.
Okay, we have. I see that we're down to 24 participants. 24 people are willing to listen a little bit more.
That's not bad.
We're still alive.
Or at least they left their computers on anyway. So this is a little more fun. It's about actual betting. And this past year, in the spring, I was doing a lot of work studying betting games in casinos in the 19th century. There were two popular betting games. One, of course, was roulette, but roulette only came in around 1800. And the roulette, there was, because before roulette, people did not, the idea of roulette had been around for a long time, and some people did it, but it wasn't very popular because people did not trust the wheels. You know, roulette wheels can be unbalanced, so the casino could be cheating. And but the roulette in around 1800, the roulette that we know today came in. And in that roulette, it's still played this way in American casinos. The European casinos have changed it a little, so there's only one pocket for the house. But in what was introduced in 1800 and still used in the United States, you could tell me about other countries. I think in general, Europe still uses the 2 pockets for the house or the casino. So there are altogether 38 pockets. 18 of them are red, 18 of them are black. So you could make all kinds of bets. You could bet on an even number. You could bet on the right side of the table or the left side or whatever, but you could also bet on red or black. And red or black was the traditional bet. The simple bet was red or black. So the casino has a little bit of an advantage because the red and black, the probabilities for red and black are both just, are both 18 out of 38, which is not quite 50%. So there's a 5% advantage for the casino. But it's still an even money bet. You put down $1, you either lose your dollar or get $1 back if you bet on red. Same if you bet on black. So it's an even money bet, even though the probabilities aren't really 50-50 because the house has a 5% advantage, approximately. Now that game, before that game became popular, and still even after it became popular, there was another game that was very popular that is more advantageous to the bettor because the house only has about a 1% advantage. And this was a game that was evolved to have a way of betting on red or black. The simplest bets in this game and the main bets in this game are also either red or black. This is a tablecloth that was used for the game. So this game was played in fancy casinos that were legal. Those fancy casinos were in what is now Belgium and Germany. which were then which were then sort of kingdoms and principalities and independent towns within the Holy Roman Empire. They were not legal in France. There was a lot of betting in France, but it was theoretically illegal. And sometimes the police would try to enforce that. This is a tablecloth that you would put down on a table to do the betting. So because it's a tablecloth, when the police are on their way, you can easily put it in your pocket. No, we were just sitting around having a cup of tea. We weren't gambling. So I'll show you a more fancy table for red and black. The idea of red and black, of betting on red or black, evolved from the French playing cards. Now, nowadays we talk about heads and tails. How many of you would, let me look at the list of participants. How many of you would trust a coin flip in a casino? Raise your hand if you would trust a coin flip in a casino. 2 people raise their hand?
You got to have guts to trust it.
You need to come to my casino because it's, you know, a lot of magicians know how to make a coin come out the way they want. And the coins are biased in the first place. Percy Diaconus wrote a nice little article with his collaborators about what the natural bias is in a penny. And the coins in the 18th century, you can imagine, were very imbalanced. So you might talk about flipping a coin, but nobody's really going to bet on it in a casino. They don't. But another way of betting, I mean, I think most people wouldn't, even with their friends, they wouldn't trust a coin flip in those days. When I gave this lecture elsewhere recently, or a related lecture, I used this example. I asked, did anybody actually ever bet on a coin flip that they believed was fair? And I got one guy that said, yes, he had bet on a coin flip that he thought was fair. And I said, who flipped the coin? He said, I did. So, okay. Okay, I can understand that.
But did he won in the end?
Pardon?
Did he won his bet in the end?
I don't know. I think I didn't ask that. I don't remember. But another way of betting that people did between friends was they pulled a card at random from a card deck of cards. Nowadays, we're all accustomed to these 52 cards. Half of them are red, half of them are black. You know, there's ace, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, king, queen. We all know that story. And there's 4 suits, hearts, spades, diamonds, clubs. But these actually were French cards, were introduced by the French in 1400. The Chinese had invented playing cards half a millennium before that, and all the other countries had their own kinds of playing cards. It was only France that used these red and black cards, but nowadays we all use the red and black French cards because the French were such great gamblers and they made such wonderful games that everybody wanted to play their games. Right. And these casinos, even though they were not in France, the language of the casinos was French because gambling was French, especially among the elite. So this standard deck of cards, the natural way to make a 50-50 bet would be to choose a card at random from that. Is it red or is it black? That's what your bet is. But in a casino, you're not going to trust the cards either. Any magician can pull whatever color they want to out of a deck of cards. So nobody's going to trust the casino on that deck of cards. So they needed to make up a game where you could trust the casino. And that's where red and black came from. And here's how you did it. You actually took 6 decks of cards. You took 6 decks of 52 cards each, shuffle them all together. So you got 312 cards and let everybody shuffle them. Everybody in the game can shuffle them and reshuffle them and cut them. So you're all convinced that they're as random as can be. Then you give them to the dealer, who's called the tailleur. You give them to the dealer and he deals 2 rows of cards. One row is called red and the other is called black for no good reason, except the people wanted to bet on red or black. That's what they were accustomed to. So they want to bet on red or black. So you call one row red and you call one row black. And in each row, you stop dealing when the sum is bigger than 50 on the faces. So you add up the faces of the cards. You know, is ace counts as 1, the face cards counts as 10. So you get if you get a king, queen, and jack in a row, that's already 30. One more card, no matter what it is, will put you over 30, so you stop. So you do that for both rows. And the row that gets that's total is closest to 30. You stop as soon as you're bigger than 30. So it's going to be something between 31 and 40. If the one that comes closest to 30 is the winner. If it's red, red wins. If it's black, black wins. And so you win depending on whether you bet on red or on black. Now, if there's a 31 to 31 tie, the casino gets half the money. That's where the casino's 1% comes from. It's just a little more than 1%. If it's a tie that is not 31 to 31, if it's a 32 to 32 tie or 40 to 40 tie, you just ignore it and go on to the next round. But there is a little advantage to the casino, which is so small that we can practically ignore it for the things we're talking about. So here was the tablecloth again. Here's where the guy that dealt the cards stands, and he just deals the 2 rows of cards right here. And to bet, you're sitting around the table or standing around the table, and to bet, you put your money on the green. And generally speaking, you're going to bet more than once. This is a card the first deck has 312 cards on it. So that first round only uses some of those cards, and then the next round uses some more of them, and eventually you use up the whole deck, and then you start with another deck. So you play all morning. You play for a few hours like this, and then in the afternoon you have another round. In the evening you have another. You know, the casino might do 2 or 3 a day. Probably not in the morning, just in the afternoon and evening. In the morning you're recovering from last night. So you put your money on the green, and if you win some money, you probably keep it on the green. But if you lose all your money, you might need to take some more out of your pocket and put it there, or borrow it from a friend, or mortgage your farm, to the casino in order to have more money to keep betting. And when you bet, you take whatever you're betting and push it into the black. And then when it's over, if you're betting on black, you push it up here on black. If you're betting on red, you push it over here on the red. Okay. And then when the bet is settled, the guy here standing here, he's called the croupier. He has a big rake, and he rakes the money away from the people that lost and rakes the money towards the people that won. And if the money goes to when the money is collected by the bank, by the casino or the house, he puts it right there. So there's a little, to make it a little more complicated, if there's a 30 to 31 tie and you're going to lose your money or half your money, you say, wait a minute, I want to have a redo. So you push the money into a further box. So that's why there's more boxes there. But that's too complicated. Here is an elegant picture written by a gambler in 1820 of the elegant tables that he bet at 30 years before. And he used to be a bettor, but he got over it, and then he did other things. And in his old age, he needed money. So he published a book about it. And he was an artist too. And he wrote this picture. Here's a fancy picture, huge. This has enough room for about 18 people to sit around it. Maybe you can see the numbers of the seats, and other people can stand in between them. The ones that are seated keep their money in this little slot, in this little hole here. And then they could advance their money into this guy. This guy here has put that money there. And there's some money that was pushed farther in, and so on. This is the casino's money here. These are the 2 rows of cards here. This is a rake the croupier uses. These are extra cards here. These 2 things here are lamps. Fancy, very fancy. They were very elegant casinos. Now, the problem is, so what do I want to tell about this? What I want to tell is about the betting systems that people used. The casinos would actually, you know, quietly maybe, or would tell people, here's a system you can use and you might win doing this. So they had these betting systems that were sometimes very complicated, and sometimes they looked like they could win. It looked like they would multiply the money you had by quite a bit, that you could make good money. You could make a good return on your investment. But the trick was the difference between the amount you have in your pocket and the amount you put on the table. Why is this relevant to to game theory probability? Because our fundamental principle of testing by betting is you got to put all your money up front. You can't keep adding money. If you keep adding money, you're cheating, and you can make it look like you've multiplied your money by a lot if you just keep putting more money in until you win. You're taking a big risk, but if you can manage to keep putting money in until you finally win, you may make yourself look very good. And basically, betting systems did that, and they were deceptive because you weren't comparing the amount of money you had in your pocket that you could have put in. You're comparing it to the amount of money you actually put in. And when you do that, it looks like you're getting a very good return on your investment. This is a temptation when you're testing by betting. That's why I spent so much time saying, don't do that, don't know that. You got to put all your money up front. And the temptation, we see that temptation in the casino, and we see that temptation in business. We see it all the time. People are losing, they're behind, they put more money in. They go out and find an investor and put more money in. And if they succeed in that way, were they good business people? Were they investing in something that was smart, or were they just gambling, even at bad odds? Even if you're gambling at bad odds, the casino has an advantage. But even if you're gambling at bad odds, you've got a very good chance when you do this kind of thing of getting a good return on the investment that you think that you seem to have made, rather than the one that you were prepared to make. Or would have made if things had gone badly. And I have some slides here that define how return on investment is usually defined. Usually return on investment, when you talk about return on investment in finance, people pretend like the investment is all put on the table. It's like you deposited in the bank at 5% interest or 0.01% interest like we get now. So return on investment, if you pretend like the denominator, the return on investment, you invest K, you get a net profit of G, the return R is G over K. That's what you're taught in business school. That's the idea of return on investment. But if the investment amount is random, because you put more money in when you lose, and you create a negative correlation between the amount of money you put in and the gain, in that case, the return on investment, even though the expected value of the gain may be zero, the return on investment will be positive. And sometimes it's positive enough that you can get very deceptive results. I just have a simple example of the D'Alembert, and I'll stop here because we're 20 minutes past. What do we have going on now? We now have 24 people still have their computers on, but I'll stop anyway after this slide. This describes probably the most popular betting system in the 19th century. You start by betting $1. Well, in the European casinos, it wasn't $1, it wasn't €1, it wasn't £1 It was what was it, like maybe a louis. If you're at the rich table, it's a louis. You invest 1 louis. When you lose, you increase your bet by a louis. Every time you win, you decrease it by a louis, unless you're back down to 1 louis. You don't go below 1 louis. You always keep betting 1 louis until you finally stop. But if the previous bet was 5 louis and you win, the next one is only 4 louis, and so on. And then you stop when you're 4 louis ahead or after 50 bets, whichever comes first. If you do that, the expected return is more than 100%. You expect to more than double your return, and you have a 98% chance of winning. And the house advantage of even of a roulette, 4 to 5%, doesn't make any difference. Doesn't make any practical difference to these numbers. What it does is that it makes, what is the pitfall of this is that in the cases where you lose all your money, you never get 4 units ahead. You just get farther and farther behind. And after 50 bets, you quit and you've lost a fortune. It adds up. You've lost a fortune. So it's the only thing the house's advantage does is that it makes the fortune you lose bigger. But these numbers don't change much. So this is very deceptive. You tell somebody to do this, they go out and try it. If when you have a 98% chance of winning, the chances are like 80% that you'll win 4 or 5 times in a row before you lose. So this is very deceptive. You know, people play it 4 or 5 times in a row and then they lose a fortune. So the practical question is, how often does this happen in business? Or government, for that matter. Government sometimes has projects with cost overruns, as you know, and other projects that have to be abandoned after you sink an immense amount of money in it. So the government official that is who had the brilliant idea of doing the project because it would be a wonderful thing and pay for itself, are they a genius or are they just lucky? This, you know, I'm not answering the question because the question would be different in every case. But it's something that we should look at more in finance. Marco, thank you very much. I see I said that I would stop, and so let me say, maybe you could say goodbye for us until tomorrow, or until the people in the garden, so-called, if you.
Yeah, there might be people in the garden. I think I thank you very much for your lecture today. It was really fantastic. Yeah, let's give it let's give it up. So a round of applause, please.